So let us begin Lagrange multipliers. This is a technique that actually helps us to minimize or maximize a function if we have constraints. Again, this is another method for optimization. Lagrange multipliers. So let me give you an example. Suppose you own a company and that company produces these plastic boxes. Well, okay, as you can see, it has a volume and you're interested in maximizing the volume of this plastic box. So this is your goal. Maximize the volume of the box. Okay. Well, so you need to have some materials. You need to have a device, a big machine, a plastic injection that actually creates this. So you need some raw materials, all right? So think about the cost of the raw materials. You cannot spend too much money on the materials and you have some contracts with some other companies that provide those raw materials for you. So you have a constraint on the price of the raw materials. We also have a constraint on the price of the raw materials. Now, what is X? What is Y? What is Z? To maximize the volume. How do you calculate X, Y, and Z? So these types of questions gave rise to the new method, Lagrange multipliers. In this method, we have a function. Think about it as the volume of the box, volume function. You're trying to maximize or minimize that function. We also had a discussion about that. So suppose you try to optimize, maximize, or minimize a function, and the function is z equals to f of x and y. But at the same time, we have a constraint, like the price of the raw materials. Also, there is a constraint like function g x y equals to a constant c. So the price is fixed. You cannot change the price. So you have a constraint function. Then we take the gradient of function f and we set it equals to lambda, the gradient of function g. So this is the gradient of f, and this is the gradient of g of function g, and this is actually related to the Lagrange technique. This is just a number, a constant, and using that equation, you're able to solve for x, y, and if your function has z as well in 3 variables, you're able to use them to find those values. So why we set them equal to each other? When you have a constraint function and you find the gradient, we're interested in having the gradient of the function which is vertical, perpendicular, orthogonal to function g to be in the same direction as the gradient of function f, which is orthogonal, perpendicular to function f as well. So by setting these equal to each other, it means that these two vectors, you have two vectors. Vector 1 is proportional to vector 2. To the second vector, vector 2. So remember that the gradient of a function is orthogonal and perpendicular to the surface at the given point. By setting these two equal to each other, it means that we can find the points that actually help us to optimize this question. How to maximize the volume by using the price constraint and so on. Example. This example says, well, find the maximum, minimum values of function. What is our function? Our function is f of x and y, z equals to x squared plus 2y squared on the circle, on the unit circle. On the unit circle. Very well. So, for example, we're trying to maximize or minimize this function, and we know that the constraint here is the unit circle. It's bounded to unit circle. Very well. The equation of unit circle is x squared plus y squared equals to 1. Since this equation is defined, let us use it as g of x and y, which is x squared plus y squared minus 1 equal to 0. So this is my function f of x and y. Let us use the method of Lagrange multipliers. Of course, you can use elementary calculus method to optimize this function. We can write y in terms of x and plug that in here. You get a function in just one independent variable, take the derivative, set it equal to 0, find the critical value, and that gives you the maximum or minimum value of the function. But since we are in multivariable calculus, we prefer to use the methods that we just learned. So this method says, hey, take the gradient of function f, set it equals to lambda, the gradient of function g. Okay, the gradient of function f, we call that the gradient of f is equal to, it's a vector, f of x, comma, f of y. So this time, this vector is 2x, comma, 4y, equals to lambda, the gradient of function g, 2x and 2y. So what do we have here? We end up with two equations like this. We are setting two vectors, the components of two vectors equal to each other. Two vectors are equal if and only if their components are the same. If V1 is A and B, V2 is C and D, V1 is equal to V2 if and only if A is equal to C and B is equal to D. We're using the fact that we learned before. So here you have 2x equals to lambda 2x, and you have 4y equals to lambda 2y. We have two equations. So what are the values for x, y, and lambda? What would be lambda? What would be x? What is y? Perfect. So let's see what do we have here. The first equation, I'm just focusing on the first equation. By solving the first equation, I have two cases. Lambda is equal to 1, because if I cancel out 2x, lambda is equal to 1. Or if lambda is not equal to 1, x must be 0. Or x is equal to 0. Okay. What about the second equation? In the second equation, lambda cannot be equal to 1. Okay, there is no way. In this case, we can say, hey, I can cancel out y, and lambda can be equal to 2. Well, either lambda is equal to 2, or if lambda is not equal to 2, y is equal to 0. Two cases here. But how do we decide? We're going to use the relation that is already given to us. We know for any x and y, we must have lambda squared plus y squared equals to 1. We have a nice equation, and we're going to use it. Now we use x squared plus y squared equals to 1, the constraint that is given to us. If x is equal to 0, what do we have? Well, if x is 0, then y is plus minus 1. Okay. What if my y is equal to 0? If y is equal to 0, then x is plus minus 1. So how many points do I have? How many critical values I get? I get 4 critical values. 0 and 1, 0 and negative 1. 1 and 0, negative 1 and 0. Okay, I have my x and y values, but what is z? To find z, I have to get back to the original function. If x is equal to 0, y is equal to 1, my z is equal to 2. If x is equal to 0, y equals to negative 1, again, my z is equal to 2. If x is 1, y is 0, my z is 1. And if x is equal to negative 1, y equal to 0, z, the original function, is 1. So what is our conclusion? At 2 points restricted to this circle, my function is maximized. At 2 critical values, by using this restriction, the function is minimized. maximized at 2 points. Again, all of these are restricted to this function. If we eliminate this function or use a different function, we don't get these values. And here you have minimized at 2